Hello, everyone, and welcome to our next webinar in which we're going to pick the brain of Dr. Kebbe. Today, we have a very special webinar organized in which we're going to take a deep dive into what is probably one of the most interesting topics when it comes towards big data. We're going to have a look at some of the most common algorithms in big data analysis and analytics solutions. I'm super proud and happy to present our next speaker, Dr. Ibrahim Kebbe, who is a Big Data Framework Ambassador and a lecturer at Advisors in Saudi Arabia. Dr. Kebbe, it's my great pleasure to welcome you back again, and thanks so much for hosting this webinar. I really look forward to it.
It's good to be back. Thank you. So, hello, everybody. Today we talk about some common algorithms underlying the analysis of big data and all the analytical solutions, all the analytics solutions that are actually encapsulated in the analyst and the enterprise big data framework. Why? First of all, let me talk about myself. My name is Ibrahim Kebbe. I have a PhD in Systems and Information Engineering from Hokkaido University in Japan, and have over 2 decades experience in construction, health care, oil and gas, manufacturing, telecom, and education. I'm a full professor and a researcher in the areas of management science, business analytics, and AI. I instruct a lot of material that are pertaining probably to the industrial engineering concentration, plus some applied mathematics courses. You can see the badges that I have over there. The badges related to my certifications, concentrated both in enterprise big data on one hand and in project management and on the other hand. So my background is an engineer, but this background has actually allowed me to delve into AI and analytics, especially that businesses as well as academia is actually becoming more and more data driven. In this sense, it was natural for me to shift my focus to big data analytics. So why should anyone be interested in this webinar? Well, you hear a lot about data science and data scientists. The thing is that when you are dealing with data is like an ocean. The water actually takes you wherever it wants. Sometimes, but you can actually work your engines, you can work your sails to direct yourself in this data-driven world. But the fact is that since you are data-driven, it means that there is a great influence of the data on the way you find your decisions, the way you make your decisions. So in this case, it would be, and at the sound of being too academic in this case, it would be very interesting to realize that many of the practitioners in data science are detached from the analytical theory, from the background of analysis, in the sense that they rely heavily on pre-encapsulated libraries and that you find in languages like R and Python and so on. These libraries have allowed this type of detachment. Sometimes you find a problem which is too complex to solve, or it is too special because, in fact, regarding the engine of solution, the difference between one problem and the other is actually two main differences. First of all, it is the nature of that problem. What kind of nature we have for this problem? Is it an optimization problem? Is it a search problem? Is it any type of problem you might think about? Is it, for example, forecast problem, and so on. On the other hand, you also have the business objective, and the business objective by itself will actually imply that sometimes you will find what out of kilter solutions or out of kilter problems. That's exhibit the same assumptions that other problems exhibit. For example, one problem might be taking, for example, having an underlying assumption that, for example, a certain parameter is constant. But what if it is not? What if your data is autocorrelated? And what if your data is not autocorrelated? How will you, for example, decide on what to do? In this case, the difference between problems resides in assumptions that you make about these problems. The more assumptions you make, the more risk you take up on one hand, but on the other hand, the simpler the solution is going to be. So it is the job of the data scientist to actually pick and choose among these matters. In order to be able to pick and choose, one has to go back to the tree of knowledge, to the origin of this knowledge, and see what these libraries, what these functions are all about, and what kind of assumptions actually govern them. By knowing these assumptions, one can actually modify, for example, certain models in order to extend them to certain problems that are not actually covered by the aforementioned assumptions. An example of that would be, let's say, for example, you are solving a supply, a supply chain problem where you have manufacturing firms and you have distribution networks and what we call distribution centers. When you have a problem like that, obviously you have supply and demand, but the demand, for example, can actually wane down, can actually decrease, but to a certain level, you have to set a certain level of decreasing of this demand in order to allow supply to be produced. So what happens in this case, we think about this problem and what kind of assumptions do we have. Let me give an example. Let's say that our distribution centers, they have decreasing demand. When we have decreasing demand, it means that obviously we would have doubts about the cost of supply. So the cost of supply in this case is going to be detrimental in the sense that you might have to shut down some supply, some supply nodes, like what happened during COVID-19. Some factories like Toyota, they had to not shut down some factories, but they had to cut down the production time within the day. They had to cut down the production time within the day because they didn't have enough demand to justify their supply. So when you have a problem like that, you have to embed the allowances of these assumptions into the problem itself. So this requires for us to go back to the mathematical, to the statistical, to the operational research origin of these problems in order to come up with new algorithms. But what is the purpose of an algorithm? As we know, an algorithm has the purpose of effectively and efficiently extract any insights possible from data, namely big data. But the problem is that if you want to get these insights, okay, these insights rely on an input. That main input is the data, the big data. This big data is random by nature, which necessitates that statistics be at the heart of these algorithms that are supposed to draw these insights. So what we have basically is statistics on one hand as a basis for these big data algorithms. And we will demonstrate how these statistics actually exhibit themselves in the various encapsulated algorithms. And on the other hand, we have some other extensions to these algorithms. For example, those extending into operations research or OR. And the operations research is mainly about optimization. So we have statistics and we have optimization and whatnot. And all of that would actually lead on to algorithms that are heuristic in nature, in the sense that they exhibit the same solution promotion that we see in recursive optimization problems. But on the other hand, they also have this statistical element that looks more or less like a simulation. All right. So these algorithms, of course, they find themselves into three main applications. We use them mainly for calculations. On the other hand, we use them for data processing, wrangling, cleaning, and stuff like that. And finally, a combination of both, we find them in automation. They are supposed to automate our work. Speaking of which, automation, here we are going to see a gallery of staple algorithms. We are going to display these algorithms one after the other, and we are going to discuss these routes that I've mentioned before. So the first, if you want, the first batch of these staple algorithms is the EDA, exploratory data analysis. Well, exploratory data analysis is something that relies on extending some exploratory insights. That's to say, the insights that you get from EDA are not final. We use them for the exhibition of data, of raw data. We use them in order to visualize how this data is actually behaving. So the graphical behavior of data is displayed in order for us to have an idea about the nature of this data and the phenomenon behind them. For example, if you display, let's say, data about, for example, charging loads, power charging loads in in a solar system, in a photovoltaic system, in a PV system, you will realize that, and when we look at the batteries, for example, they are going to exhibit a behavior which is not linear. Their behavior is mainly exponential in the way that the battery fills or depletes. So when you have something like that, that would be, let's say, for example, you have data pertaining to sales, and you realize your sales are behaving asymptotically, meaning that you are heading towards a certain, a certain limitation to how much the market is actually buying. So saturation, we call it saturation. So market saturation is not linear. It is more or less asymptotic, more or less exponential. Well, on the other hand, if we go back to the classical origins of exploratory data analysis, we see it often used in research methods, specifically in the grounded theory. The grounded theory is a type of exploration that is finding a hypothesis. That's to say, contradictory to many other problems in big data analysis or in research. Usually, research starts with a question. It starts with a hypothesis, an assumption, and that this assumption is either verified or nullified. Well, in this case, we don't have a hypothesis to start with. We rely heavily on data, and this is by far the meaning of being data-driven. We rely on data in order to tell us what kind of questions are we supposed to ask, or what kind of direction we are supposed to be heading in. So this is applied, this type of approach is applied to parametric determination, determining, for example, parameters about the economy, determining parameters about certain trends, and so on. And it is also used for shortlisting your options. For example, if you have a multitude of options, you are going to see which options are actually ranking highest. And of course, it serves as finding parameters that are meant for cutoffs, like what is the cutoff value to determine whether or not a certain state is actually reached. So in this case, if we look at the background of such EDA, it is actually applied in classical statistics by, for example, exhibiting statistics about the data sets. And what I mean by statistics here is I'm talking about averages, I'm talking about standard deviations, I'm talking about percentiles, ranks, and also proportions. So, for example, when you're talking about some data sets that are supposed to exhibit a certain behavior, for example, those statistics that are related to the, they call them the growth curves. The growth curves of infants. You find them in doctors' offices, in pediatric medicine. So these charts are actually based on exploratory data analysis. So you find percentiles and ranks for example, to see how the child is growing, and in terms of weight and in terms of height. So this is exploratory data analysis. So far, we haven't done any analysis yet, but we are exploring. We are trying to see which questions are actually meant to be answered by a certain analysis. Then we have the statistical inference. In here, in this case, we are talking about the hypothesis. We already have an established hypothesis, and we either test it or we find the confidence intervals for the statistics that are described in this, or that are the subject of this hypothesis. Now, the difference between statistical inference and EDA is that, as I said, EDA is something that actually starts, that ends with a hypothesis, whereas statistical inference starts with a hypothesis. Statistical inference is based on sampling error. What we suppose is to have is that this data set that we are actually using for analysis, this data set by itself is a sample of a larger data set that we cannot actually get hold of. So this is a keyhole. They call it a keyhole approach. We are trying to generalize whatever conclusions we can have about a sample. We are trying to generalize that on the whole population. So the classical approach, first of all, is to set the difference between the null hypothesis and the alternative hypothesis. And it is subject to type 1 and type 2 error in case one makes the wrong decision, or that's to say, makes the wrong choice about the hypothesis by refusing it, let's just say rejecting it while it's correct, or adopting it while it's wrong. So in this case, classically speaking, when it comes to statistics, we always have used the null hypothesis was represented by a normally distributed population, usually normally distributed. And it is a distribution of sampling errors. It is a distribution of sampling averages. That's to say, if we were to pick a very large number of the same samples over and over again, that's to say we are sampling and resampling from the same population, we are supposed to have a distribution that is more or less normal. And this is actually mediated by four hypotheses. It's mediated by four hypotheses that we find in classical statistics, the last of which is the central limit theorem, which necessarily states that the sampling distribution of a non-normal population is considered to be normal as long as this population goes over, for example, 20 or 25 individuals. But when you talk about 20 or 25 individuals, talking about big data, we have a huge population of individuals, in this case of data points. So the central limit theorem is taken for granted. That's to say, the results that we are going to get there are taken for granted. So we don't rely on these hypotheses, meaning that we don't actually have to commit to finding a probability distribution that corresponds to the null hypothesis. I mean, your null hypothesis in this case is no, but you don't have to actually search for data in order to have this distribution statistics, for example. Some of the problems that you find in classical statistics in this particular inference is whether or not we know the error distribution. That's to say, the standard deviation of the population. If the standard deviation of the population is not known, then we have to go to, for example, t-distribution instead of Gaussian distribution or normal distribution. Well, this problem doesn't exist when it comes to big data. In the big data approach, what we do is simply we simulate the null hypothesis distribution. That's to say, we don't need to know the average of this distribution. We don't need to know the standard deviation of this distribution or anything about it. All we need to know is the sample that we have, and then from this sample, okay, we start simulating other samples and make a sampling distribution out of them to represent this null hypothesis. And this is something which is done by a library in R or Python or any other programming language, which means that it is something which is already prepackaged. So this type of replication will actually save us a lot in terms of population parameters determination. We don't have to go through the many complexities of statistical inference, classical statistical inference. But again, this is the origin of the problem, the origin of the problem. So as you can see, we have solved an age-old problem when it came to making statistical inference, and that's only because we are actually relying on large data, on big data. So we have seen two classes of algorithms so far, EDA and statistical inference. We now look at correlation. Well, correlation is based on the usually based on the Pearson correlation coefficient rho or R. Rho when it's considered with respect to the population, R when it is considered with respect to the sample. Again, this is the root in classical statistics. And as we all know, this correlation coefficient could be either positive or negative. So we have positive correlation or negative correlation. In positive correlation, both X and Y, and the independent and the dependent variable, are both moving in the same sense, in the same direction, in the same sense. Meaning that if the X increases, so the Y will increase. For example, like the years of experience, as they affect the dependent variable, which is the salary. So you get a salary according to your years of experience. So this is a positive relationship, because as the years of experience increase, also will increase the salaries. On the other hand, you have negative relationship, which means that when the independent variable increases, the dependent variable is going to decrease. Like, for example, the size of debt as related to the, for example, as related to the reliance of the borrower, or for example, let's say productivity in terms of productivity in terms of lack of sleep. The more sleep you lack, the less productive you are going to be. So, and of course, when we talk about correlation, in this case, correlation doesn't actually care about the data being linear or otherwise. It cannot be, correlation is something which is just showing to show how well the data is knit together, how close the independent variable is to the dependent variable in terms of predictability. Okay, and of course, when we say predictability, we don't mean causation, because correlation doesn't at all mean causation. So, what is the origin of the of classical mathematics in this case? Well, the fact of the matter is that on one hand, the Pearson correlation coefficient is a statistical. It is a statistic. It is a statistical parameter that can be calculated from any data set. On one hand, on the other hand, this same coefficient can be actually subject to validation. Why? Because the correlation factor is a representation of the average correlation within data. That's to say, it is an overall correlation. It doesn't pertain to each point or each data point alone. So it is a sort of, it is a sort of an average. And as we know, average can be consolidated or otherwise by comparing them to their standard deviation. In other words, you could have strong correlation or weak correlation. And this strong correlation or weak correlation correlation doesn't have to do much with the shape of the data, rather with the dispersion of the data itself. So this can be actually validated by a hypothesis test on its own. And you can have this is what we usually do when we have a weak correlation. Okay, when we have weak correlation, whether or not we actually fixate this correlation is by reducing it or subjecting it to a hypothesis test. This hypothesis test is going to tell me whether or not I can actually trust this type of correlation, no matter how weak it is. For example, a correlation factor of 0.5 or 0.6 sometimes are very meaningful, depending on whether or not it actually passes the hypothesis test. The next topic is, or set of algorithms is any algorithm which is related to regression. And in this case, we have multiple types of regression, linear or otherwise. So what regression does is that it adds trend to correlation. That's to say, let's say we have proven that we have a correlation set within a certain data. Very well. Since we have this correlation doesn't actually tell us how, for example, how we can actually mediate to find, because by the end of the day, this is a fractional, or this is a continuous data, and the subject for regression is usually continuous data, and it is supervised learning. It belongs to supervised methods, in the sense that we need to have some training data first in order to set the model for us. But with these training data, where do you get them? You get them from the data set itself. Data set itself is actually, it has actually the independent versus the dependent variable. But in case we are trying to intercept or, for example, interpolate for a certain y, for a certain dependent variable value, and we have the x, for example, you have, for example, this is the data that you see here is data about salespersons inside a company. We took a small sample of these salespersons, and we have seen how many years they have spent to the company, plotted against the sales that they have made in thousands of dollars. When I have something like that, it would actually mean that if I have somebody with certain years of of employment, but I have no idea about their sales, I can actually, let's say this person belongs to a different department. I know how long that person had belonged to that department, but I have no idea about his or her size of sales. What I can do is I can interpolate for that. And in this case, I need to have, to begin with, a trend. Let's say, in this case, the trend is manifested in the slope of the regression. That slope of the regression by itself is a number. It's a rate that I can use in actually to calculate that calculate a predicted or regressed information, okay, about the sales. But on the other hand, this trend as well will be subject to this. That's to say, in classical statistics, it will be subject to the same scrutiny that regression, that correlation has actually been subjected to. In this case, the hypothesis test will be saying whether or not that trend is actually something that you can rely on. Let's say, for example, you have a very small trend, a very low trend. Why? Because of the dimensional difference between x and y, between the independent and dependent variable. In this case, in this sense, it means forcibly. For example, the example you have here is in the x is maximum 10, okay, whereas y is in the hundreds. So when you have something that different, okay, and we don't make any type of normalization, then in this case we would expect numerically the slope to be very, very small. We expect to have a very small slope. Okay, so in this case, what does it mean? It means that when we have a you know, a different you know, a different problem, in a different problem where you have the x's in a very large numerical range and the y's in a very small range. In this case, forcibly, my slope is going to be very small, in the order of 1/100 or 1/1000. So when you have a small slope like that, it doesn't mean that it is not significant. So size doesn't mean insignificance in this case. So significance is actually passing that hypothesis test about that slope. It will actually consolidate to me whether or not it is reliable for me to actually rely on this slope in order to make, you know, you know, expectations or predictions. A good example of that, is when you have, for example, predictions about how long a patient is supposed to, how much a patient is supposed to spend on a medical procedure. Let's say somebody has an open heart surgery and they go into hospital. So in this case, you can think about two interested parties. You have the patient himself or herself, and you have the insurance company. Both of them are interested for different reasons. The patient is interested because he or she would like to have an idea on how much money they are supposed to spend, while they are staying at the hospital. Okay, on one hand. On the other hand, the insurance company is interested in knowing the same information based on the fact that they have to set their premium. The premium for insurance has to be set. Now, the thing is that when you come to thinking like that, those two different perspectives, they bear on different margins of error related to regression. What do I mean by that? As you part from the average, from the centroid of this data, your expectations or your predictions are going to be weak. That they are going to be less than perfect. But this margin of error is very large with respect to the patient. That, for example, for the patient, that margin of error would, for example, would lie in the thousands of dollars, whereas for the, as you can see from the below graphic, you have those large differences between the margin of error for the cost. This is not for the company, this is for the individual. But for the company, it's a difference of a unity, of a unit number under the square root in the original formula. It means all the difference. As you can see, those margins are very tight, very small, because the company doesn't look at an individual case. It looks at the average of multiple cases that they have in their history. So in this case, we see that regression is utilized basically in prediction. But when it comes to the quality of this solution, one has to look further in the classical statistical background in order to consolidate that type of prediction, I guess this is something that one can embed inside the libraries that are you know, responsible for these calculations. But again, this is an idea that actually resides within the classical statistics. On the other hand, even if your regression is not linear, there are many ways to linearize them, or for example, incorporate an approach that actually accommodates polynomial regression. And in case it is an original nonlinear approach, well, that has its own merits as well and its own methods in classical statistics. So this is as far as the regression goes. Our next algorithm, here we have started with you know, with more or less discrete data. The data that we have here are now not necessarily whole numbers or continuous numbers. Okay, so we have classification. Classification is a supervised pattern recognition method, meaning that you have to have training data separate from scoring data. So scoring data, they are applied on the model that we generate from the training data set. And that training data set is going to give us the basis of which, in this case, the classes that are actually made by that training data. And then we expose these classes to the new coming data, which is not yet classified, in order to classify them. So again, when you look at different classification algorithms, you see here about 5 of them. These different algorithms, they have their own approach. Each one of them has a different approach than the other. And but in this case, we start first with the k-nearest neighbor. Well, in the k-nearest neighbor, what we basically do is we have already a trained data set. We have a data set which is already classified, for example, class A, class B. So it is already classified. And we have a newcomer. What we do is we connect this newcomer to an odd number closest neighbors to that newcomer. For example, let's say that we have a single scoring data thrown inside this data set. So what we do is we say, okay, where are the 3 nearest points around this data, the pre-classified points? What are the 3 closest pre-classified points to that, closest to this new data point, or 5 nearest, or 7 nearest, and so on? What we are having here is a vote, and you realize that k here is always odd, because for a good reason, for to have the scale tipping in on one side rather than the other. So in this case, you say, okay, if we find, for example, a higher fraction or a higher ratio of these, for example, these pre-classified points being closer or closest to that scoring point, then we say that this scoring point belongs to the class of the majority. So what is the majority in this case? The majority is the fraction of points, nearest points, that belong to either classes. Now, if we look at the origin of such classification, we see that it doesn't find itself in classical statistics, but rather in the networks, in the operations research networks. There are network problems that are solved in operations research, and these network problems, they are just problems that lend themselves to a network topology. So when we have this network topology, like the one that we have here, what we do is we use an algorithm that is based on optimization. We optimize the closest points. So this is a minimization network, and by all means, most network, the overwhelming majority of network problems in operations research are minimal cost networks. So this is exactly what we are doing. We are setting up a minimal cost network between k neighbors with relation to a central point, which is that newcomer, the scoring data, the new scoring data. So this is one origin of one method. Next, we have the naive Bayes method. Again, it is a naive classifier because it has the weakness and the advantage at the same time. It has the property of not being aware of the interdependencies between independent variables, because every data point might have multiple characteristics that we call independent variables, and these independent variables will be used in classifying these points, if you will. They will be used in classifying these records into one or more classes, into or more classes. So in this case, naive Bayes is naive in this sense, but the advantage of such a method is that it's very light. That's to say, you can use it as a rough estimation. It is very fast, and very nimble. In this case, the origin here are statistical. Okay, they are statistical origins that are used in general decision-making theory or general decision-making. It is based on Bayes inversion. It is based on Bayes inversion, which belongs to non-classical statistics. In other words, when you have introductory courses to statistics, usually these topics, the Bayes inversion, is considered an optional topic because it doesn't belong to classical statistics. It has a different approach because classical statistics are based on sampling, whereas Bayes inversion is not based on sampling. It is based on description. That's to say, when you have conditional probabilities, when you have a conditional probability, like, for example, the probability of being, for example, of such a trait, having such a trait, and belonging to such a class. So in this case, classification is connected by a conditional by a condition to the characteristic of the person or the data point carrying this trait or this characteristic, which means that the probability of a data point to belong to a certain class, that probability is actually an inverse probability. It is converted from conditional probability to posterior probability. I'll give you an example. Like the data that you collect on college students, whether they smoke or not. Okay, so the classification here is not about the gender of the person or the student. It is about whether or not that student smokes. Why? Because gender is something which is innate into a person, and it is something which is apparent. Whereas when it comes to being a smoker or non-smoker, this is a behavior. Smoking or not smoking, it is a behavior. It is an action. It is not a trait. It is not a pre-existing trait. So in this case, we would have, what interests us is to, let's say, by the end of the day, we are interested in knowing, for example, what is the proportion of males and females among smokers. Let's say we here are taking the perspective of a cigarette company. That cigarette company would like to make a promotion special for men and one special for women. So what they do is, what they are interested in is what is the proportion of men and women within smokers. But the service that they collect brings them different data. It brings them the proportions, that's to say the probabilities, the proportions of smokers among men and smokers among women. Why? Because when you, for example, when you are surveying, when you see a man or a woman, you'll ask them, are you smokers or not? When you have this, it means that the conditional probability is the probability of smoking with respect to gender. The probability of smoking with respect to gender. It is not the other way around. And you are interested in the inverted value. That's to say, the probability of smokers among a certain gender. This is what you are. What you are interested in is the proportion of the gender within the smoking population. This is what you are interested in. So you rely on this type of inversion in order to get it. How do we use it in classical decision making? We use it in determining the sampled or the imperfect value of information. That's to say, information that you collect from, as we said before, from from surveys or from trials or from pilots or from even the opinion of experts. These sampled data will actually influence the way you think about your decision. That's to say, it influences the probabilities about the decision. So we talk about these probabilities being modified these probabilities being modified by Bayes inversion. That's to say, let's say we have a certain decision, and this decision goes 50-50 in either directions. So this is like voting. This is a very weak vote. This is a very weak decision. So what we do is we need to tip off the scales. We need to tip the scales by what? By, for example, conducting an experiment, and that experiment will give us conditional, conditional probabilities. We will invert them in order to be able to use them in that decision that we make, like decision trees or such. Well, there are many examples here. For example, this happened. It happens a lot when somebody is looking to, is afraid of sanctions and looking for a decision whether or not to flee a certain country or to send their money abroad. What they usually do is they get, and they don't have much to go on. They don't have enough information to go on. What they will do is they will bring the bearer of bad news. They will hire a lawyer who has a strong visibility on the indictment, and that lawyer is going to give them new odds, and these odds are going to be integrated in the decision using Bayes inversion in order to tip off these 50-50 risk. So that risk will become maybe 80-20. In this case, they will have something to go on. So this is the classical route of naive Bayes. Then we have the logistic regression. Again, the logistic regression, it is a binary, non-parametric binary classification method, in the sense that it is yes or no, it is go or don't go, and so on. Lease or buy kind of decision, a binary decision. So what it does is that it isolates parametric regression, okay, from non-parametric regression. So this is in classical statistics. In classical statistics, there is no logistic regression. We don't use logistic regression. But what we do is this. Logistic regression, I'll give you an example of that. You remember what we said, the years of experience, okay, or the years of employment against salary. This is a positive relationship. And when you make a regression out of it, in most cases, this regression, what I mean, not logistic regression, the regression that we mentioned before, that regression is going to have a weak correlation, or the hypothesis test for the slope is going to be inconclusive. Why? Well, one problem would be the problem of small data. But suppose that you have large amounts of data, and you make this regression, and still it is weak. What is the problem for that? The problem is that there are certain classes of data inside that data set that are distinct by themselves from one another. For example, in that data set that we talked about, the years of experience against the salary, you might be talking about a mix between men and women. And we all know, for example, that on the average, salaries of women are less than salaries of men on average. So in this case, one would wonder, why would we actually mix the data like that? We should actually make a distinction between males and females when it comes to salary. One approach would be to make one regression for the ladies and one regression for the men. But if you keep them within one data set, you should be able to make a distinction between them. What we do in big data, for example, when you use the logistic regression, we are forfeiting the element of salary in this case, and we are concentrating on the element of gender. It's like when you give a certain salary, for example, when you quote a certain salary with a certain combination of years of experience, the logistic regression is supposed to help you classify that person as being a man or a woman, for example. But in classical statistics, we didn't have to do this type of isolation. What we do simply is we split the slope of the regression. In this case, the slope of the regression is actually the parameter that shows you the strength of correlation. That's to say, the trend. We make one trend for one gender and another trend for the other gender, or what we call a differential trend. What do I mean differential trend? It's a trend or slope which is modified by a binary variable. Yani it's like this. You have, for example, the slope. Let's say the slope for the salary of men multiplied by X, which is years of experience, plus a certain differential slope modified by what? Modified by a binary variable. When this binary variable's value is 1, this item or this trend is actually added to the regression, showing, for example, the salary of a man. But when it is 0, this difference disappears because binary variables usually modify the value of their own coefficients, not the other way around. So when we have that, it will disappear. Yani when the binary variable is going to be 0, obviously this differential term is going to disappear. By having that, then we will automatically be able to see the trend for what? For the salary of women. So this is how classical statistics used to approach this type of combining the logistic regression with the normal regression. The fourth classification, or the fourth classifier we take into consideration here, is the classification trees. Again, classification trees, they utilize a different approach. They utilize an energy-based method, basically an entropy-based split, a method of making a differentiation between classes based on entropy. So an entropy here is based on the gain of insight. For example, as the name suggests, when we say classification trees, what you're doing is you are splitting these data points. You are splitting them into caches, into isolated caches. You keep on splitting them, and every time you check this sub node, for example, this sub node that, for example, contains a certain amount of data, you check them for entropy. When entropy is high, or when you have entropy inside this subsystem or inside this node, you realize that there is still energy inside. There is still energy inside. There is still conflict inside. Conflict between what? The conflict between classes, which means that more classes actually exist in this node. So what you will do is you will split it further. As you split it further down the line, you will realize that entropy is going to decrease in the nodes. Once you have 0 entropy all over the place, it means that you have actually succeeded in making the separation between all these classes. Obviously, this is not binary. Of course, we here rely on many classes. But as you can see, this split is actually based on entropy. A good example of that is when you have mixed nuts. When you bring mixed nuts, when you have mixed nuts, you have the small nuts and you have the big ones. You have the small ones and the big ones. When you try to shake the jar of these nuts, when you shake the jar, what happens? The larger nuts go up and the smaller nuts go down. Okay? So it depends on which one you want to get first. So if you want to get the big ones first, by shaking, what is happening is that these nuts are moving between classes. They are moving between levels. And this motion is caused by entropy. Once you have a stability reaching that distribution, that's to say, when you have the large ones on the top and the smaller ones on the bottom, no matter how long you keep on shaking, it is not going to change its formation. So this is an entropy-based mechanism. And well, NUTS is the closest thing I had on my mind. Finally, we have a classifier which is very well rooted in classical statistics, which is the LDA, the linear discriminant analysis. The linear discriminant analysis is a binary split between two classes, and that split is mediated by a line. It is mediated by a line. That's to say, what we are looking at is a line, a straight line that would actually cut between the two classes. An example of that would be, let's say we have two variables. One variable would be, let's say, would be the height, and another variable would be the weight. What is the effect of height and weight with respect to being classified as male or female? Again, in this case, what we see is that usually men are classified to be tall and heavy, or taller and heavier than women. So we'll have a kind of segregation. Of course, this segregation is not complete. That's to say, about these split lines, you wouldn't have 100% purity of split. You might find a lot of big women to be wrongly classified as men, and small men to be classified as women. This happens. But what we are looking for is actually the line that comes closest to that type of description. And then we will sort out the special cases later on. The point is that this supervised classifier is mainly based on the multiple analysis of variance, where we try to find homogeneity maximized about between the, within the classes. The same class has to have a homogeneity which is higher than before, and we try to increase this heterogeneity across classes. So what we want to have is a class that is well conformed with itself, and classes that are very far from one another. So what is the approach that we use in this case? Usually we use the as I said, the analysis of variance, multiple analysis of variance, in order to set this differentiation. And for anybody who worked with it, with the multiple analysis of variance, they must have seen, for example, have used the F statistic, which is the ratio of the standard deviation between the difference among classes and the difference within the classes. What you try to say is, if this ratio actually exceeds, we do a hypothesis test for it. If this ratio of the homogeneity over heterogeneity exceeds a certain limit, that differentiation is meant to be substantial in this case, and we say, okay, yes, we have actually reached a clear split between the two classes. So this is the origin of classification algorithms. Then you have clustering algorithms. In this case, in clustering, it is also discrete, but opposite to classification. Clustering is unsupervised. Unsupervised in the sense that there is no training data and scoring data. All the data is considered to be as one. For example, let's say that you have applied a clustering algorithm on a certain data set. This clustering algorithm is going to cause some kind of pattern within this data set. Throw in one or many scoring points, and these scoring points will become, or this scoring data will become automatically part of the whole, and they are going to reshape the model. The model is going to be reshaped. It is going to be changed again. So what does it mean? It means that the application of this particular scoring is going to change the model substantially. It becomes part of the model. And this is the heart of having unsupervised methods, they change all the time because of the modifications that applies by adding scoring data. So we are going to discuss two types of clustering methods and how they relate to classical mathematics. First, you have the hierarchical clustering, which is necessarily dispersed points, and then these points are joined little by little they are clustered little by little until they form one big cluster. As you can see, the great cluster contains two separate clusters, and these two separate clusters, they contain subclusters and so on. So if one is interested in a two split, the clusters are already there. If one is interested in four splits, again, this split is already identified in this type of cluster. Now, this type of clustering belongs to operations research. Classically, it belongs to operations research. It belongs to the network type of problems that belongs to constrained optimization. That's to say, what we are applying here are we are applying constraints. Those clustering borders that you see that are engulfing the data points cluster by cluster, this is called a constraint elimination. It is called a constraint elimination. That's to say, by the end of the day, when you have a single cluster, it means that you have eliminated all your constraints. A classical example of that would be what we call the constraint relaxation problem. The constraint relaxation problem. When you have a problem which is over constrained, what is the problem with an over constrained problem? An over constrained problem doesn't have any solution. This is the problem, because it doesn't have any feasible area. So there's no optimal solution in this case. So what we suggest is that, well, the reason we have that is that our problem or our model is overburdened with constraints. Let's try to get rid of some of them. So there are many ways to do that. The most classical way is to relax these constraints by introducing binary, what we call linking constraints. What these constraints do is they eliminate, they eat up, or they eliminate other constraints. Like, for example, you have a problem with 15 constraints, and you want to get rid of at least 7. You want to get rid of at least 7 of these constraints. So the problem leaves you with a solution. The model leaves you with a solution where you have less constraints than before. And then you can actually visualize a solution within that new, less constrained problem. So this is hierarchical clustering. On the other hand, you have k-means clustering. K-means clustering is, first of all, it is the number of clusters are fixed. You need to determine the number of clusters from the beginning, and it is mediated by the relocation of, let's say, relocation through recursion of the locations of centroids of these clusters. And it happens like that. You see, for example, to the left in green, you have 5 data points as an example. You have 5 data points, and you say, okay, let me make 2 clusters out of them. Let me make 2 clusters out of them. So you decide already that you need to have 2 clusters. Okay, so what you will do is, to begin, let's just say this is an initial condition. It is true that you have 5 points, but what we'll do is you will assume, because you see, assumption is valid in this case because we have recursion. That's to say, the solution is reached through trial and error. Of course, it's not the blind trial and error. It is a convergent method by the end of the day. Convergence is guaranteed. So what you'll do out of these 5 points, you will pick randomly 2 centroids because you decided that you want to have 2 clusters. Okay, pick up 2 centroids. Let's say, for example, we take point 3 and point 4. We take point 3 and point 4 as what? As our pseudo-centroids, the beginning centroids. Okay, in this case, what do? You have 2 points that are 3 and 4 against the other points 1, 2, and 5. So you calculate the distance between them, the Cartesian. This, of course, you have more than the Cartesian representation. You could have many other types of representations, but let's look at the Cartesian. You take a Cartesian distance between these two centroids and the three other points, and see which centroid is actually closer to which point. So in this case, you find out that, let's say, 4 is actually closest to 3 is actually close. 4 is actually closest to 1, and 3 is closest to 2 and 5. So you decide that, okay, now I have two clusters, 1 and 4 on one hand, on the other hand, 2, 3, and 5. Okay, since you have these clusters established, now you find their centers, and their true center. Their true center will be a point which is distinct of them. That's to say, you will find the centroid of the 1-4 cluster and the centroid for the 2-3-5 cluster. Once you find these two centroids, okay, you will find their distances with respect to the other 5 points, with the 5 points, with the original 5 points, and determine which one is closest. In this case, you find that the formation of the clusters have actually changed. Now 3 is connected to 5, and 4 is connected to 2 and 1. So the formation of the clusters have changed. If you try to do this, now you have two different clusters, that's to say 2 different centroids. You find these 2 centroids and you apply what you have applied before, you reiterate, and you find that the centroids don't change their clustering. The clustering doesn't change, which means that you have reached your balance point. Again, when it comes to operations research, this is called an energy method of optimization, and it finds itself very well in heuristic methods like simulated annealing, for example. It's a good example of clustering. So this is as far as clustering goes. Next, we have the outlier detection. Again, the interest in outlier detection is to detect what is abnormal, what is abnormally away from a certain, commitment or class. It is like a strong to weak cluster relationship. In this case, that applies a lot in fraud analysis, in detecting money laundering, in detecting foul play, and so on. In this case, we have 2 algorithms that are elected. You have the GRUBS outlier detection and the k-nearest neighbor outlier detection. GRUBS, on one hand, relies purely on hypothesis testing, which is classical statistics. Normality is assumed in the data, which is fair enough, and the data point, which is intercepted by the smallest p-value, as you can see from the histogram on the left, that smallest p-value, it actually corresponds to the point that it will be considered as an utmost outlier. That is to say, if you can actually find a point under that p-value, under that very small p-value, which is in this example 0.02, which is 2%. 2% is considered to be very small. Then, by all means, this is considered to be an outlier. If you want to enlarge your continence of outliers, and you will allow for a 5%, for example, outliers, you will find more outliers. Obviously, when you increase the allowance, you will have more outliers. So this is GRUBS outlier detection. On the other hand, you have the k nearest neighbor. In this case, you might say k farthest neighbor. It is the inverse of clustering, and it is based on the maximization between of the separating distance between a main cluster and the outliers. Now, when it comes to operations research, obviously this is not something that belongs to energy methods and distance methods and entropy methods. They don't belong to statistics. Rather, they belong to operations research. In this case, we talk about an inverted assignment network. An assignment network is a network that assigns a certain value to a certain data point. When we find, for example, usually assignment networks are used in order to resolve bids, business bids, contracting, bidding, the assignment of projects, the assignment of employees even. When you have a method like that, it is called inverted because in this case, it is not looking for minimal assignment, it is looking for maximal assignment. It is looking to find what is the farthest assignment we have or designation we have from the network that we are considering. So in this case, KNN fits the bill actually. And actually the methods that are used in this case, the method of distance, for example, is something that we use for the inverted assignment network. Finally, we have data presentation. Well, someone might argue that this is not an algorithm, but I would say that this is communication. We need to report our findings at the end of the day, because an insight doesn't actually serve you at all if you cannot actually, if it's not visible to the decision maker. And that's it. So dashboards are used in order to facilitate the insight grasping for decision makers, and it will help a lot in report visualization. So I guess this is all I have for today. I hope that you were not bored, and you are welcome to ask me any question.
Thank you so much, Dr. Kebba. For me, this was a perfect webinar.
Thank you.
And I learned by listening to you. We have received a couple of questions in the chat on the left-hand side. So for people who still want to ask questions, by all means, feel free to do that. The chat is still open and you can do that. So let's start looking at some of the questions that have come in recently. First is, in big data, you assess the traits and attributes of data to discover trends and aspects, and you have done that by showcasing a number of different algorithms. Question that is asked right here is, who selects the right kind of algorithm? Is that a data analyst or data scientist? What's your thoughts on that?
Well, the data analyst deals with a preset number of algorithms. That's to say, they know, for example, that if you need to do clustering, you have these many choices. If you need to, so what they do, the analyst actually has the capability of putting the problem at hand and the data at hand in the right library, if you want, of algorithms. But when it comes to deciding on designing the algorithm, this is, of course, the job of the data scientist. The data scientist will actually work on two types of problems. If you have first the problem of the cost of the algorithm, and you have the problem of the insight quality, the quality of the insight. In this case, let's say that you have a problem and you have a lot of data. So let's say, for example, you have a classification problem that bears on more than 2 classes. So what you will do is you will use, for example, what we call a rough SEV. In this case, a rough method, which is very light and very quick. Like, for example, using the naive Bayes classifier, because they are very fast. We use them in order to settle our preliminary classes. And then what we do is we apply more specific and more quality methods to the results that we've had from there.
Now, if I'm summarizing what you're saying, can I say that an analyst uses existing algorithms, so kind of the ones that you explained in the lecture, whereas the scientist is more involved in creating new ones? Is that how I should read it?
Exactly. New ones, and not only new ones, but combinations of old ones. That's
so that means that if you want to be a data scientist, you first need to know the ones that are in existence.
You use them like Lego blocks.
Yeah, well, I think that that's also one of the reasons I liked your lecture so much is in just a little under an hour, you gave an overview of some of the most important algorithms that are out there. And I think with those building blocks, you can start to see what's applicable and create new ones. Good. I still have time for one or two more questions. So let's see if that's possible. Next question that comes in, I think this is one to pick your brain on as well. How is big data and analytics different from standard business intelligence? Does it provide any form of different decision making? And if so, what is it?
Okay. So business intelligence is not about processing the data all the way through. In other words, an application of business intelligence, for example, is exploration. For example, you can explore data by using, for example, Excel or Power BI or whatever you want. By doing such a thing, you are relying on the visualization of the original data sets in order to come up with a preliminary conclusion, not a final conclusion. The final conclusion is left for analytics. That's to say, analytics are going to use more thorough algorithms and methods in order to find the minute insights, those faint differences between data points. Besides, multidimensional, if you want, multidimensional decision making is maybe not facilitated much by business intelligence, because business intelligence doesn't actually look into the details. Let me give you an example. Many businesses have found by business intelligence, if you look, for example, for certain business and for the competitors, let's say, for example, making furniture, the furniture business, you realize that in furniture business, in almost all countries, the firms or specialized furniture, like, for example, kitchens, you find a curve like that, an exponential curve. This exponential curve, if you look at it from the viewpoint of business intelligence, it would look as if, well, business is actually growing. We have a place in this market. We should go there. But in fact, if you look closely, beyond business intelligence, if you apply your analytics, you will realize that it is true that they are moving in the same direction, but at the same time, they are branching in specialties. You have different types of business branching. This is why they look many, but if you look truly through them, if you classify them, you will find many differences between them. And 20 or 30 years ago, there used to be a small amount of these businesses, but they used to do everything. Now there are too many of them, but they are doing so little. They are being working in subspecialties. So business analytics will never see that.
No. Could I say that if I listen to you correctly, that analytics kind of goes one step beyond business intelligence? And thinking your slides, what I just saw is more of the business intelligence, more of the exploratory data analysis, whereas analytics is more around applying some of those clustering and classification algorithms that you talked about.
Because at the end of the day, small differences between what, for example, business intelligence shows you certain data set or data clusters that look the same. To them, they look the same, but if you explore them or if you analyze them using analytics, you will see a large difference within them. It's like if I want to say it, those 3D frames that they put in some museums or art exhibits. If you look at it from one side, you will see one thing. If you look at it from the other side, you will see a different thing. Business intelligence shows you just one perspective, whereas business analytics, it shows you a moving perspective. That's the idea.
Well, I think that that is a very good quote, and I think that that will also be a perfect end of our session today.
Thank you.
Dr. Kebbe, as always, it's such a big pleasure to talk to you. You're so knowledgeable, and you're also able to relate very complicated topics very, very quickly. So it's always a pleasure to have you here and to listen to you. Thanks so much for your participation today. One of the other comments that I saw in the chat is if you could also organize a session around explaining AI algorithms, which I think is a very good idea. So we'll take that in mind. And I hope to see you again soon. Thanks so much for your time today.
Thank you very much.